Okay, today we're going to discuss percent composition and empirical and molecular formulas. Alright, when we're talking about percent composition, it's a mass percent, and we're looking at the mass of a component of the substance divided by the total mass of the substance. If it just asks you to find the percent composition, then typically they're wanting the percent for every single element that's in the compound. Sometimes, like in this example, it's just wanting one particular component, in this case the carbon. It wants to know what the percent carbon is in MSG. So the first thing we're going to do is we're going to figure out what our total mass is, and that is essentially, total mass is just our molar mass of the compound. So just to kind of review what we did in the previous section, we would find our molar mass by adding up the individual molar masses of each of the atoms that's in the compound. So let's see. So 60.055 for the carbon, 8.064 for the hydrogen, 14.007, and 63.996. So if we add all that up, I get 146.122. So that is the grams per mole of MSG, and that is also, that's going to be our total mass. All right, this piece right here, that is our component mass, or our mass of our carbon. So my percent composition, or in this case percent carbon, is going to equal 60.055, the mass of the carbon, divided by my total mass times 100. And that's going to give me 41.1%. Okay, now let's take a look at chemical formulas of compounds. If you remember from before, the formulas have two components. We have the element symbol, and then we have subscripts, and these subscripts tell us the mole ratios of each of the elements that's in the compound. So example, if NO2 is our compound, that says I have 2 atoms of oxygen for every 1 atom of nitrogen, which also means that for every 1 mole of the NO2, I have 2 moles of oxygen atoms to every 1 mole of nitrogen atoms. Okay, so if I know that I can figure out what that set ratio is, then, or if I have information to figure out what that mole ratio is, then I can use that to determine the formula of the compound. Now, in talking about formulas, there are a couple of different kinds of formulas that we're going to deal with. Empirical formula is just the formula that represents the smallest ratio present. For example, if we had H2O, that is an empirical formula. However, H2O2 would not be an empirical formula. Its empirical formula would just be HO, because it represents 1 to 1 would be the empirical. Ionic formula, those are always empirical, just by the way that we defined a formula unit for an ionic substance. The formula unit is the smallest ratio of the elements in the substance that defines what the substance is. So formulas for ionic substances are always going to be empirical. A molecular formula is the formula of the substance as it exists in nature. So above here we talked about how H2O2 would not be an empirical formula. However, H2O2, which is hydrogen peroxide, that is an empirical formula. That is how that substance actually exists. Okay? H2O for water, that is both the molecular and the empirical. It is the simplest ratio, and it is exactly how that substance exists in nature. Okay, so thing to remember as we move into how do we calculate empirical formulas is that the subscripts in the formula represent mole ratios and that they are always going to be given in whole numbers. Okay, so that's key to this process we're going to look at. All right, to get an empirical formula, here is the basic procedure that we're going to follow. You're going to find the mass in grams if it's needed. Sometimes they will give you the mass of each element in the compound. Other times they're going to give you a percent composition, and we'll look at what you do if they give it to you in that way. Then you're going to take those grams of each element and convert them into moles. Then you're going to divide by the smallest number of moles to get the simplest whole number ratio. Okay? If you were taking a math class, this third step, they would call it normalizing. Okay? But here we're just going to call it divide everything by the smallest number. And then if after you do that you don't get whole numbers, you're going to look for a number that you can multiply everything by to get them into whole numbers while still preserving the ratio between each of the components. And again, we'll talk a little more detail about this process. It'll be clearer as we go through some examples. Okay. Here is a rhyme that I came across to help you remember the process step by step. One of the biggest mistakes I see people do is that they'll start through the process and they'll skip a step. So the rhyme to help you remember the steps are percent to mass, mass to mole, divide by small, times to whole. All right, so kind of come back to that as we go through the process of solving. All right, so here we have a brown gas, which is an air pollutant, is found to contain 2.34 grams of nitrogen and 5.34 grams of oxygen. We want to know the formula for this substance. And of course, with this type of information, the best we're going to be able to do is the empirical formula. So we already have them in grams. All right, so I usually write them this way on the page, and you'll see why here in a minute. All right, then convert it to moles, mass to moles, the second step. So we're going to do our molar mass of nitrogen and molar mass of oxygen. And so we get there 2.34 divided by, so 0.167059. And on this step, you really want to carry the values out at least 5 or 6 digits. The reason is that sometimes if you round these too early, you'll over-round and you'll get the wrong ratio. So don't round these until the very end, these values. So in this step, we're going to carry them out just to make sure that we don't round past any of our ratios. So 0.33396. Okay, so this is moles. Now we have each in moles. Now I'm going to normalize these values, or essentially divide each by the smallest, which should get me a whole number. And so we get this is going to be 1 there, and then this one 396 divided by 0.1. Whoops, I keep putting that in wrong. 67059. That's going to be 1.999, which is approximately 2. So when we get to that whole number place, if it's very close to a whole number, you can go ahead and round them. And what this says is that my formula then, these are my subscripts, is NO2. Okay, and that is an empirical formula, and that is also a molecular formula. Okay. Now, here's an empirical formula if we have a percent composition. So say here I have 60.8% sodium, 28.6% boron, and 10.6% hydrogen. Okay, if it gives us percent composition, essentially what we're going to do is we're going to assume that we have 100 grams of this substance. And so if I have 100 grams of the substance, I'm going to have 60.8 grams of sodium, 28.6 grams of boron, and 10.6 grams of hydrogen. Process is still the same. First step is convert to moles. And boron is 10.811. And this one is, sodium is 22.98 grams. All right, so then we're going to calculate our moles, and again, carrying it out 5 or 6 places, 2.64578. 2.64545. 10.559. Okay, so our smallest value is this one, so 2.64545, 2.64545. This one is 1. That one's going to give us a 1, and so that's going to give us 3.975, which is about 4. So my formula then is going to be NaBH4 for that. Okay, now let's take a look. We'll move right along here. Whoops, forgot that was there. All right, looking at molecular formulas. Remember we said molecular formulas are the formula as the compound exists in nature. And so to determine whether or not something is a molecular formula, it could possibly be reduced to a simpler form. All right, this question says which of the following could be an empirical formula. That means it's already in its simpler form. So in looking at these, N2O4, that's not the simplest ratio, and so that could not be an empirical. If it had to find its empirical, we would just reduce it down. So NO2 would be the empirical form of this of N2O4. Same thing here. NH3 would be the empirical of N2H6. N2O5, that is the simplest ratio. So N2O5 would also be the empirical. So this is the only one of those that could be an empirical formula. Now, how do we find it? Well, in order to calculate a molecular formula, you need two things. You need the empirical formula, and then you also need the molar mass, the actual molar mass. So in this example here, we're working again with NO2 as the empirical, and it says that we have a molar mass of 92 grams per mole. All right. essentially, to find the molecular formula, I want to know if the empirical is the same as the molecular, or if it is some multiple of if the molecular is some multiple of the empirical. And so what we're going to do is we're going to look at the actual mass, the molar mass of the empirical. So the molar mass of NO2 with 1 nitrogen and 2 oxygens is about 45.987 grams per mole. And so again, what I want to know is I want to know how much bigger is the molecular than this empirical. And so what I'm going to do is I'm going to take the molecular weight of the actual molecule, divide it by the molecular weight of the empirical, and I'm going to round that. That's going to give me, it should be approximately a whole number, and that is about, this one is about 2. So that tells me that my molecular formula is twice as big as the empirical. And so all I'm going to do then is take the 2 and I'm going to multiply each of the subscripts in the empirical formula by 2. So N2O4 is the compound that we're talking about. It has a molecular mass of 92, and it has an empirical formula of NO2. Alright, the last thing we're doing is something called combustion analysis. And again, this is a typical analysis that would be done in a lab to determine the composition of an unknown substance. And in this case, it's an unknown substance that contains carbon, hydrogen, and possibly oxygen. And so just to give you a little background, so you'll kind of know where these values that we're going to use are where they come from, we have a substance, and they put it in like a little chamber here, okay? We're going to feed some oxygen into that chamber and burn the substance, okay? The products of that reaction are going to be passed through a water absorber and a CO2 absorber. If you remember from some just basic chemistry, when we burn a hydrocarbon, all right, if I have a compound with carbon and hydrogen in it, and I burn it, and remember in chemistry burning just means we're combining it with oxygen, okay, and the products are going to be H2O and CO2, all right. That also applies if there is oxygen in this initial substance as well. Our products would still only be H2O and CO2. Now, the key thing to remember in our method of solving this is if we look at our unknown substance, all right, here is the carbon, and what do we notice about our products? Well, we notice that all of the carbon from the substance is going to end up in that carbon dioxide. And similarly, all of the hydrogen from that reactant is going to end up in the water. And so if we know how much water was produced, I can go either through a factor label calc or through a percent composition calc. I can find out how much hydrogen was in the original carbon based on how much water was produced. Same thing with the carbon. I can look at how much CO2 was produced and determine from that how much carbon was in the original component. Now, if there was oxygen in the original component, I couldn't do a straightforward calc like that, just because in order for this substance to burn, I'm actually adding oxygen to it. And so the oxygen that's in the water and the carbon dioxide can come from the oxygen that I'm feeding into the apparatus, or it could have been part of the initial compound if the initial compound had oxygen in it. So we'll add a little step to figure out the oxygen. But essentially the thing to remember is we're really only calculating an empirical formula, and when our data is given to us this way, where we have a mass of water and a mass of CO2, that there's just an initial step we have to do to get it into a simple empirical formula calc. All right. So again, we're going to convert the data that we get, which the data we're going to get is going to be grams of water and grams of CO2. Okay, we're going to convert that into grams of carbon, hydrogen, and oxygen if we know it's present in the substance. Then we're going to determine the empirical formula the same way we did before. And then if we know the molar mass, we can use the empirical formula with the molar mass to find the molecular formula. So we're just kind of adding a little thing up front with this. So let's look at an example problem. Here I have a compound, trioxane, which has carbon, hydrogen, and oxygen. And the data, I have two experiments. One where they did, they burned it and got a certain amount of water and carbon dioxide. And then the second experiment, they found the molecular mass. So first we're going to look at this data here. And to go from grams of water to grams of hydrogen, you can do it one of two ways, and either way is perfectly fine. In general, I'll just show you here. I have 10.477 grams of water, and I can use just regular factor label. Molar mass of water is 18.015 grams to 1 mole of water. And then for every 1 mole of water, I get 2 moles of hydrogen. And for 1 mole of hydrogen, I get 1.008 grams of hydrogen. So I can work it out that way. 10.477 divided by 18.015 times 2 times 1.008. And so that gives me 1.172 grams of hydrogen. Or the other way I could do it is I can use the percent composition of water. So I know that I have that in water I have 2 hydrogens for every whole water. And if you calculate the percent composition, that comes out to be approximately 11.2% hydrogen in water. So the other way that I could calculate this is I could do that if I have 11.2 grams of hydrogen in 100 grams of water, then I have X grams of hydrogen in 10.477 grams of water. Okay, now that, so we have that times 477. So that gives us the same exact answer, 1.172 grams of hydrogen. So you can use the percent hydrogen in water, or you can use the factor label method, either way, to get from grams of water to grams of hydrogen. And it's similar for CO2. In CO2, let's see, I have 1 carbon. So the percent, there's about 27.3% carbon in CO2. And so if I do similarly that times my, or the other way, I can use that percent, 0.273 times my grams of CO2, 25.612 grams of CO2, and that's going to give me 6.992 grams of carbon. All right. So either way, or I could have done just a factor label to get that same answer. Whichever way you want to do it is fine. The essential thing is you want to get down to where you have, there's my grams of hydrogen, here's my grams of carbon. Now, this also said I have oxygen in it. The only way to find the oxygen is, I know I had 0.471 grams of the total of my unknown substance. Okay, minus the 1.172 grams of hydrogen minus the 6.992 grams of carbon. the remainder is the oxygen. So minus 1.172, 6.992, and so that gives me 9.307 grams of oxygen. All right, now I have my 3 components there, and I'm going to copy these down so that I can move to a clean slide here and work the rest of this problem. So then this is the only new part, because from this point on it's going to be a regular empirical formula calculation. So let's transfer these numbers. So I have from before 1.172 grams of hydrogen. I have 6.992 grams of carbon, and I have 9.307 grams of oxygen. Okay, so same process as before. Convert it to moles. Remember to carry it out. Don't round it too soon. Okay, so here's our smallest. It's going to be 1. That's going to be about 1, and then this one is going to be approximately 2. So my empirical formula then is going to be H2O. All right, and then I'm going to have to go back a slide here because I didn't write down my molar mass. Molar mass is 90. All right, so now I'm going to go, my molecular weight is known to be 90. And the mass of my empirical is 30.026 grams per mole. So if I take my mass here divided by the mass of the empirical, that's going to give me approximately 3. So my molecular formula is equal to C3H6O3. You just multiply the subscripts by the 3. Okay, now in this initial discussion we really didn't come across any problems where these numbers here were not close to whole numbers. Tomorrow in class we're going to look at some examples of what do you do when those numbers are not close to whole numbers. And so I will take any questions that you have on the stuff that we've covered in here, and then we will add on to this discussion tomorrow in class by looking at how you deal with when those numbers are not whole numbers in that final calculation.